Hello, everyone. Welcome to the Colloquium. This is my first time hosting a Colloquium, and I'm really excited to be hosting my friend and collaborator, Ariel Procaccia from Carnegie Mellon University. Ariel obviously does super fantastic work at the intersection of so many different fields, specifically CS theory and machine learning. I've recently been trying to get him excited about robotics and motion planning. Ariel has a long history of really great work and many awards, including the Distinguished Doctoral Dissertation Award, Computers and Thought Award, as well as the NSF Fellowship, and many, many, many Best Paper Awards. My favorite interaction with Ariel was often when we would drop our children off at daycare, and then we would chat as we walked back to our respective offices. One of those chats actually led to a really interesting paper that we ended up writing together about how you can be incredibly lazy in motion planning, just like you can be incredibly lazy in life. And I think that really exemplifies Ariel's sort of fantastic breadth as well as depth. He's incredibly curious about every topic, as well as incredibly deep. The first motion planning paper that I sent him, he sent me back a reply with such deep insights that I realized that I myself had to learn a lot more about motion planning, which was, I thought, my field of expertise. So I'm really, really excited to welcome Ariel Procaccia. So please join me in a hand of applause.
Thank you so much, Sid, for the kind introduction. I'm super excited to be here. Thank you all for coming. So the topic of the talk today is computational social choice. I'll start by telling you a bit about what social choice is before we talk about computational social choice. So social choice is an area of economics and mathematics that thinks about how to aggregate individual preferences or opinions towards collective decisions. Computational social choice, you can think of it as algorithms for accomplishing this task. Now, I also want to tell you about another area called fair division, which deals with fairly dividing stuff. So computational fair division will be algorithms for fairly dividing stuff. Now, if you ask an economist, they will tell you these are two different areas, but for sociological reasons, computational fair division is seen as part of computational social choice, which will be pretty convenient for me because I want to talk about all of this stuff under one umbrella of computational social choice. So putting my AI hat on for a minute, in multi-agent systems, people have had a long-standing interest in computational social choice. And the thought behind it was that as we build the foundations of multi-agent systems populated by autonomous agents, we need ways for these agents to make joint decisions, to allocate computational resources, and that's where computational social choice will come in. In fact, if you look at my PhD thesis from 2008, the title is Computational Voting Theory of the Agents, by the Agents, for the Agents. And this is really taking this pretty agent-centric viewpoint that what we're trying to do is help the agents using this type of tools. But what I've realized in the last few years is that the killer app, or at least another killer app, of the area of computational social choice is actually helping people and not software agents make joint decisions. So that's going to be the theme of the talk, and I'm going to illustrate it to you, or try to illustrate it to you through two websites that we've worked on. And my goal will be to tell you a bit about the models, the theoretical models underlying this work, and a bit about the theoretical results that make these websites possible. Okay, so I'll spend most of the talk talking about fair division and Splitit, this website. Splitit was founded in November 2014. It's a not-for-profit website. That's really important for me. And really, the idea is to help people fairly divide stuff. So the mission is actually twofold. The first part is just taking methods that were developed in my group, but also by others for fair division that were very theoretical, and making them accessible to people. The second goal is outreach, so just telling people about the beauty and power of computer science, mathematics, and economics through this topic that I think is pretty intuitive, that people can pretty easily relate to. So the slogan of Splitit is provably fair solutions. And the idea is that for each one of the applications, for each one of the algorithms, we give rigorous guarantees about what we will provide to people, rigorous fairness guarantees. Right now, there are 5 applications on Splitit for dividing rent, fare, credit, goods, and tasks. So I'm going to focus on 2 of them, on rent division and goods division. These are maybe the 2 things that we've worked on the most, but really all of these applications have attracted quite a bit of our effort and time. So I'm going to start with rent division, which I think is kind of a very intuitive, paradigmatic example of fair division, and also the most popular application on Splitit. And I'd like to motivate it through a true story. So this happened in 2001 when I was starting my undergraduate degree at the Hebrew University of Jerusalem. And the plan was to share an apartment together with 2 friends. Nir Ben Moshe was today a professor of philosophy at the University of Illinois at Urbana-Champaign, and Nomi Sender, another friend of ours. And as things turned out, when it was time to actually look for the apartment, Nir was taking this long trip in South America. So Nomi and I ended up looking for the apartment alone. And we found a really nice apartment close to campus. The thing to note about it is that it had 3 bedrooms, but one of them was clearly better than the other 2. It was a bigger room. It was like a corner room, so it had 2 windows instead of 1. And when Neil came back from his trip in South America, his position was that he should get the best room for the same price that we were paying, which somehow made sense at the time. It's hard to argue with philosophers, but in retrospect, it doesn't really make sense. All right, so what I want to think about for a few minutes is what would be a really fair way in order to divide the rent. So here's an example of an apartment with 3 bedrooms. The total rent will be $10. So this is not Seattle prices, maybe Pittsburgh prices. And we're going to have 3 players, green, blue, and red. What I'll show you is the value of each player for each room. And the assumption I'll make is that for each player, the sum of values for the rooms add up to the total rent. So it's like, how would they distribute the rent according to how they value the different rooms? So here are the values for room 1. Green has value 6, blue has value 5, and red has value 4. These are the values for room 2. And room 3, everybody has value 2, 4. Now, next, I'm going to divide the rent between the rooms by assigning a price to each room. And the crucial assumption I'm going to make is that if a player gets a room that he values at x for the price of y, his utility would be x minus y. That's called quasi-linear utilities in economics. So for example, let's assign a price of 5 to room 1. And the way to read this is that the green player, if he got room 1, would have utility of 1, which is 6 minus 5. The blue player would have utility 0, and the red player would have utility minus 1, 4 minus 5, hence this x over here. The price of room 2 will be 3. So for example, the red player would have utility 1 if he got this room at this price. And the price of room 3 will be 2. And finally, I'm going to assign the rooms to the players. So room 1 goes to green, room 2 to red, and room 3 to blue. Now, I want to claim that this division, allocation of the rooms and division of the rent, the solution, satisfies a really compelling fairness notion called envy-freeness. What envy-freeness means is that each player is at least as happy with his room at his price as any other room for the price of that room. Or in other words, no player would want to swap his allocation with the allocation of anybody else. So for example, the green player has utility 1 for his room, room 1, minus 1 for room 2, and 0 for room 3, so he's happy. The red player has utility 1 for his room, it's over here, room 2, utility minus 1 for room 1, and utility 0 for room 3. The blue player has utility only 0 for his room, but he also has utility 0 for the 2 other rooms at their prices. So he's not envious either. Right, and this is pretty cool because envy seems like something that's very abstract that would be difficult to capture in a rigorous way, but this really gives us a rigorous way of reasoning about envy. And I think it's really one source of the beauty and power of fair division. Now, the nice thing about envy and envy-freeness is that it's not only a solution for this example, it's something that you can always guarantee. So we've known for a couple of decades that an envy-free solution always exists in the setup that I described. And moreover, an envy-free solution can be computed in polynomial time. Okay, so that's great news from the computer science viewpoint. It's a very compelling solution, very intuitive, and it's not difficult to compute it in practice. The problem is that even though NV-freeness sounds great so far, it's not a sufficient guarantee in order to give us intuitively fair solutions. Or like there might be situations where an NV-free solution would not be intuitively fair. So I want to give you an example like that. This is an even cheaper apartment, total rent only $3. And the players will have the following crazy values. The green player only wants room 1. Remember that the values add up to the total rent, so he only wants room 1. The red player only wants room 2, and the blue player only wants room 3. And the division of the rent is going to be even wackier. I'll just put the entire rent as the price of room 1. And finally, I'll assign the rooms like before, with 1 going to green, 2 to red, and 3 to blue. Now, I claim that this is also an NV-free solution, right? Because red and blue are obviously overjoyed. They get their favorite room for free. That's great. What about green? He's paying the entire rent. So he has utility 0, 3 minus 3. But he also has utility 0 for getting the other rooms for free because he has no value for these rooms. Right? So this is an NV-free solution. But it's obviously not what you would intuitively want to do. Intuitively, you would want to equally divide the rent between the 3 rooms, assign a price of $1 per room, and then every player would have a utility of 2. So what we actually want to do is refine the notion of NV-freeness and be able to choose among NV-free solutions to find ones that are especially fair, especially reasonable. And from a computer science point of view, maybe the most natural way of doing this is imposing an optimization objective on top of NV-freeness. So saying maximize some objective function subject to NV-freeness, or like among NV-free solutions, choose the one that is best according to some criterion. So that's the approach that I want to take. So let me give you a few examples of optimization objectives that we could try out. So one is maximizing the sum of utilities of the players subject to the NV-freeness constraint. Now, I call this the straw man solution because it turns out that this doesn't actually help refine the notion of NV-freeness because all NV-free solutions actually maximize the sum of utilities. So this won't really help us refine these notions. Another possibility, which seems very natural, is the maximum solution. So this maximizes the minimum utility of any player subject to the NV-freeness constraint. Now, when we think about making the poorest player as happy as possible, that's already something that seems intuitively fair, and we're adding that on top of NV-freeness. So this seems like a nice solution to consider. There's no objections to it. Another solution is the equitable solution. So here, the optimization objective is we look at the maximum difference in utilities between any pair of players. That's called the social disparity. And we try to minimize that subject to the NV-freeness constraint. So this is actually something where in behavioral economics, when people have done experiments, they saw that social disparity plays a big role in how people perceive fair allocations. So this seems like an argument in favor of this kind of solution. Okay, so before we try to choose among them, I just want to make a computational point, which is, you might worry that now that we've made the computation problem more complicated, we won't be able to solve it efficiently anymore. But we show that that's not the case, fortunately. So this is work with Kobi Gal, Moshik Mash, and Yair Zik. I'll give you the full references at the end of the lecture. But what we show is that the maximum and equitable solutions, and in fact, a wider family that contains both of them, can still be computed in polynomial time. So we don't actually lose qualitatively from this viewpoint when we make this, we try to choose among NV-free solutions. But now there's still the question of, okay, I showed you like 2 very nice or pretty intuitive solutions. Which one should we go with? And here I think we have a pretty satisfying answer. So what we can show is that the maximum solution is equitable, but the other direction is not true. In other words, if you maximize the minimum utility subject to NV-freeness, that also minimizes the maximum difference in utilities subject to NV-freeness, but the other direction is not true. So this says in a nice way that the maximum solution dominates the equitable solution in terms of how fair it is. And when we're trying to decide between these two, definitely the maximum solution is the one to go with. So because of these theorems, we actually, this convinced us that the maximum solution is a nice way to approach the problem. And for this reason, we deployed the maximum solution and split it in May 2015. So it was about half a year after the website first launched with a different algorithm. But, of course, the math sort of works out nicely, but this doesn't necessarily mean that people would accept these solutions as being more fair, right? So we can prove like some nice theorems, but it doesn't mean that this actually makes a difference in people's perception of fairness. So to try to answer the question of whether this actually helps, we did a user study. And the way it worked is we approached people who use Splitit's Rendivision app, and we asked them about the actual instances that they participated in. So we actually asked them about their actual values for the rooms that they reported. We just perturbed the values of the roommates to preserve privacy and also to get different results from what they got in practice. But basically their values were the same as in the real world, which is important. And then we asked them to evaluate two solutions. One is the maximum solution, and the other is an arbitrary envy-free solution that just chooses some envy-free solution without any additional constraints or without any additional things added on top. And we asked two questions. We asked them to evaluate it in terms of how happy they are with each solution, and how fair is it to everybody else. And the results were quite favorable. So I would recommend looking at the rightmost bars, which basically put all of the instances together. Things are broken up in terms of how many players there were in each instance. And we just contacted people that participated in instances with up to 4 players. But then all of these instances together in both of them. And you can see there's a pretty significant difference in favor of the maximum solution on a scale of 1 to 5. And also on an absolute scale, the scores for the maximum solution are pretty high. So, to me, this gives at least preliminary evidence that this is in some sense, the right direction to go. When we are refining the solution and actually making a difference in terms of how fair people perceive it to be. Now, another point I want to make about these experiments, which I think make them exciting, is that if you look at the literature in behavioral economics, people often set up these, this pretty non-realistic experiment where people are told there's this bunch of virtual goods. Here are your values for the different goods. And now let's come up with an allocation and pay you in some way that depends on your value for the outcome. So this kind of thing really encourages people to think about how much each person got paid instead of like the values for different things which are not really meaningful. The nice thing when we, in this case, with this data and with these users, is that we can ask people about actual goods that they care about in the real world and their actual values. So I think this makes a significant difference in terms of how people perceive fairness and the kind of responses they would give and things they care about. So this data allows us to do this kind of study, which is pretty unusual. OK, so switching gears a bit, so far we talked about Rendivision. That's one problem of fair division and split it. The other problem I want to talk about, which in a sense is even more interesting, and it's something definitely we worked on quite a bit more and has some very interesting open challenges as well, is this problem of dividing indivisible goods. So these are cases where the goods are, can be things like precious stones, jewelry, artwork. And the idea is that every good has to go to a single player. You can't take a good and break it up and give it to multiple players. Now, the assumption I'm going to make, and it's an assumption I can talk a lot about, but let's take it as an assumption for now, is additive valuations, which means that if I give you a bundle of goods, your value for all of the different goods will be the sum of values in the bundle, of the goods in the bundle. So for example, if I gave you the diamond and the statue, your value for both will be the sum of values. One thing to notice as we go, or the most crucial thing to notice as we go into the setting, is that envy-freeness is not something we can guarantee anymore. Right? Like, think even about this example in the case of 2 players. If both players really want the diamond, I give the diamond to one of them, the other would be envious. Right? So if I allocate all of the goods, I will not be able to guarantee envy-freeness. So the technical challenges in the setting are, A, what kind of fairness guarantees can we even give? Right? We want to be able to guarantee something no matter what in every situation. And the second is designing algorithms that compute solutions achieving those guarantees. So that's on a high level, the kind of challenges that we spent and are still spending quite a bit of effort on. So I want to show you some of these guarantees that we've looked at. The first one is maximum share guarantee. It's a very cool idea. So I'm going to demonstrate it to you through an example. The example will involve this incredibly valuable collection of paintings that, let's say, was inherited by 3 sisters, and I want to divide it between them. So what I'll do is I'll go to the eldest sister, and I'll tell her, look, I give you the privilege of dividing the items into 3 bundles, but then you get to choose last. Your sisters will get to choose before you. Okay, so the sister sort of has to evaluate these different goods before she makes a decision. So she starts looking at them, and well, the Mona Lisa is pretty valuable, so let's say $50. Going with a pearl earring, or also beautiful paintings, so let's say $30. The Scream is a very interesting painting, maybe not something you'd want in your living room, so let's say $3. This is actually a Jackson Pollock painting, but it looks like garbage, so let's say $2. And the rest is, some Van Goghs and some Picassos. So, very valuable collection. She gives values to all of these different paintings. And now she has to divide them into bundles. So the sister is very conservative. She thinks, well, I want to protect myself against the worst case because I don't know what my sisters are going to choose. So I better divide the bundles in a way that guarantees me as much value as possible. So that's what she would do. She would put the Mona Lisa in one bundle, the girl with the pearl earring in a second bundle, and the rest of the garbage in a third large bundle worth $20. So in this way, she can guarantee to herself a value of $20 no matter what her sisters choose. Okay, so now the sisters go ahead and choose. So the green sister chooses the large bundle. The blue sister chooses the Mona Lisa, and the red sister, who's the one who divided and chooses last, gets the girl with the pearl earring, which is a pretty good outcome. It's worth $30 to her. Her value for everything is 100, so it's almost a third. Pretty good. But now this blue sister, the second one to choose, can say, hey, I'm really unhappy with this outcome because here are my values for the goods. So at the point where I got to choose, I just had the choice between $3 and $2. If you gave me the privilege of dividing the items into goods, here's what I would do. I would divide them into bundles like this. And this way, I would be able to guarantee to myself a value of $30 no matter what. Right? So I'm really unhappy with not having the privilege of dividing the items into bundles because I got a pretty bad allocation when I was just the second one to choose. So the question is there a way to divide the items into bundles in a way that each sister simultaneously gets at least as much value as what she could guarantee to herself if she were the one to divide and then chose last? Okay. So here's the same thing a bit more formally. This notion, the value you can guarantee, is called the maximum share guarantee. It was introduced by an economist, Eric Budish, in 2011. And the maximum share guarantee of player I is the maximum over partitions into n bundles, where n is the number of players, x1 to xn. Then you look at the minimum over any bundle j, and you look at the value I has for the bundle xj. So this is I's value for the worst bundle under I's best partition into bundles. And this is, of course, specific to every player because it depends on the individual valuation function, vi. Now, for a couple of years after Eric introduced this notion, people have thought that for additive valuations, at least, we should be able to guarantee this to each player, that the answer to my question is yes. And in fact, several groups have run millions of simulations that haven't yielded a single counterexample. But unfortunately, what we were able to show a few years ago in work with Junxing Wang is that for any number of players greater or equal than 3, there exist additive valuation functions that do not admit a maximum share allocation, giving everybody at least value equal to their maximum share guarantee. So, this is bad news. The counterexample is very, very intricate. Yeah.
Yeah, I was wondering if these are more like pathological valuation functions, or do they have some bearing to someone might value like that?
Right. So the question was, are these pathological valuation functions or something you'd find in practice? So they're very, very, the construction is very, very delicate. And it's, in particular, if you perturb the values by just a bit, then you will have a maximum share allocation. right? So in some sense, it's non-robust to any kind of perturbation. However, like the significance of this is that it says that this is not a guarantee that we can give, right? So we would want to give some hard fairness guarantee. We can always give everybody their maximum share guarantee, and this tells us this is not something that we can promise users of Splitit, for example. However, in practice, we do always expect to see instances where we do have a maximum share allocation. In fact, on every single instance in Splitit, there is a maximum share allocation. And like I said, even in very extensive simulations, you can't get like a single counterexample. The good news is that we were able to relax this a bit and show a positive result. So what we asked is there some alpha, hopefully a constant, such that we can always give each player at least an alpha fraction of their maximum share guarantee? And what we showed is that the answer is yes, with alpha equals 2/3. Right, so you can always, there's a computational part to this as well, but the main point is existence. Whatever the values that you give me, there exists an allocation of the items to the players in a way that each player gets at least 2/3 of their maximum share guarantee. So, one thing I like about this theorem, I think theoretically it's quite interesting, the proof, but one thing that's really significant about it is that it was actually the basis of the algorithm that was initially deployed on Splitit for dividing indivisible goods. So the algorithm was kind of intricate. I'll give you like a simplified version of it that captures the main idea. So the idea is you first determine what's the maximum value alpha, such that you can give everybody an alpha fraction of their maximum share guarantee. And subject to that constraint, you maximize the sum of utilities. Now, in practice, alpha is always going to be 1. Like I said, every real-world example, you can give everybody their maximum share guarantee. But what this theorem allows us to do is to give, finally, a hard fairness guarantee, which is this 2/3 thing. So what we actually said on the website is we will guarantee to you, here's what maximum share guarantee is, and we will guarantee to you 2/3 of that. In practice, we expect you to get the full thing, but here's what we can always guarantee to you no matter what. So this algorithm worked pretty well for a couple of years, but it also did some really weird stuff. So I want to show you an example where it really misbehaved. This example was actually submitted by a Splitit user who played a bit with demo mode and found 2 examples that he thought were weird. The first example is not actually weird, but I want you to look at the one that's highlighted over here. So essentially what he says is you have 3 people, 5 goods. And he says everybody places 200 points on every good. That's because on Splitit you have 1,000 points to divide between the goods. So what it means is that everybody has an equal value for each good. And he says what the algorithm does is give 3 goods to one player and 1 good to each of the other players. And that's true. So what's the reason? When you have 5 goods that you value equally, your maximum share guarantee would be 1 good, because any partition into 3 bundles would have a bundle with at most 1 good. So then what the algorithm does is, subject to the constraint of giving at least 1 good to each player, maximize the sum of utilities. Now, because they all have the same value for each good, you might as well maximize the sum by giving 3 goods to one and 1 good to each of the other. Right? But intuitively, what you'd want to do is give 2 goods to 2 of the players and 1 good to the 3rd player. So that's just one example where the algorithm behaves weirdly. And examples like this are really what prompted us to think, that maybe this is not the right way to do things, and there's probably a better approach. So here's the better approach, or like an approach that I really believe in right now, at least. And it's based on a different fairness notion and different relaxation of envy freeness called envy freeness up to 1 good. So what is envy freeness up to 1 good? We say that an allocation A1 to AN, where AI is the bundle given to player I, is envy free up to 1 good if for every 2 players I and J, the value I has for AI is at least the value I has for AJ. So far, this is just envy freeness. This is exactly envy freeness. But now we relax it by adding this additional term. We remove the maximum value that I has for any good in the bundle of J. So the intuitive way to think about this is it could be the case that I envies J, but I can always remove a single good from the bundle of J in order to eliminate that envy. So we might have envy, but only up to 1 good. Right? So, this feels like an intuitive relaxation of envy-freeness, in some sense minimal, although there are even more minimal relaxations. But you could say at this point, you just wasted 10 minutes of our lives, like telling you about the fairness notion that can't actually be guaranteed. Why would you believe me that this can be guaranteed? So I want to prove to you that I can actually always guarantee this fairness notion. It's a very easy proof. So what I'll do is I'll use a simple algorithm, round-robin allocation, to allocate the goods. So the idea is that if I have n players, they're going to choose items in the order 1 to n, 1 to n, 1 to n, every time each player in their turn choosing their favorite item from the remaining items. So in our example with the painting collection, let's say the players will choose in the order green, red, blue, and green. So let's let the players go ahead and choose. So each one of them chooses their favorite item in their turn. And I want to claim that this allocation is envy-free up to one good. So let's focus on the blue player for the purpose of this proof. And what I'll do is I'll divide the sequence of choices into phases, where the first phase starts with the first choice of the blue player and ends just before the next choice. And then the next choice starts the second phase, and so on. Right, now let's look at some phase, like phase 1. So I claim that within phase 1, the blue player is not envious. She likes her Van Gogh better than the other two paintings. And of course, the reason is obvious. Like at the point where she chose the Van Gogh, she could have chosen the other two paintings. Actually, one of them is also Van Gogh, but the portrait. She could have chosen the other two paintings, but she chose that particular painting. So she obviously is at least as happy with that. And similarly for phase 2 or for any other phase if you have more phases. So within every phase, every player is not envious. Because of the additivity of the valuations, when you add up all of these values across the different phases, you will still, like this inequality in values will still be preserved. So you get envy-freeness across all of the different phases. The only catch is that the green player and the red player chose some items before the blue player ever got to choose. But the crucial point is there is at most one such item per player. So for example, if we remove this painting from the green bundle, this would eliminate any envy that the blue player has for the green player. And if we removed this painting from the red bundle, that would eliminate any possible envy the blue player has for the red player. Right? So you can always remove a single good. Yeah.
I mean, you set up very clearly that we're assuming additive values. And previously, maybe that mattered, maybe it didn't. It's an assumption, we're going to go with it. Here, I mean, round robin is all about the additive value assumption, right? I mean, if I choose one at a time, I have no opportunity to bundle anything, right? It seems almost like an abuse of additive value.
Yep. Yeah, that's a good question. So I'll just repeat the question. The question was, we've assumed additive values. This algorithm is really tailored to additive values. And one point where it came up is when I said, just look at the values across different phases and add them up. So the answer is, it's true that round robin is tailored for this. The existence of EF1 is actually true for any combinatorial valuations, as long as they're monotonic. It would just be a more complicated proof. So I like this one for additive because it's just very simple. The idea is also, it's something I could prove to you in 10 minutes. So the existence is true even for general combinatorial valuations. It will get more tricky when you think about more general combinatorial valuations. It gets more tricky on the following slide, where I'll ask for EF1 together with another property. And then even when you make things like slightly richer, then the kind of properties I'm looking for are not guaranteed to exist for richer valuations. For example, supermodular, subadditive. So definitely, I mean, there's a lot to talk about here. Maybe I'll use this opportunity to say a word about additive valuations. It's one thing that's nice about them is they make the math nice and give an opportunity to give some nice guarantees. But from a practical viewpoint, they're actually crucial because of elicitation, because it's very easy to get from the preferences from people. What we do in Split is we just say, here's a pool of 1,000 points, divide them between different items. And now we can, if we want to think about what's your value for a bundle, we just need to add up the individual values. So it's something that's very easy for people to express. By contrast, when you go to richer combinatorial valuations, it's just very difficult for lay people to express this type of valuations. So I feel like additive valuations hit a sweet spot between how easy they are to elicit and how expressive they are in terms of capturing people's preferences. So that's another argument for why you would want to go with this. Okay, kind of a long answer, but okay. So good. So we've proved that an EF1 allocation exists, but one, round robin, like we said, is tailored for this kind of setting, but also it's not a very good algorithm. And one way to see that it's not a good algorithm is it doesn't satisfy a property called Pareto efficiency, a very basic efficiency property, economic efficiency, which means that there's no other allocation that is at least as good for everybody and strictly better for some players. And the way to see this is, for example, I might give up an item that I'm getting now in order to get 2 items in the future, right? I might trade with you like some item that I got now and you really value in exchange for 2 items that you would give me later. That's sort of one example. So, this is kind of disturbing, and it says, okay, so we can guarantee F1, but we want a better way of doing it. In particular, we would just want envy freeness up to 1 good and Pareto efficiency, which is the other property I was alluding to in the previous answer. Our idea, the way we approach this, is to maximize what's called in economics the Nash welfare, which is the product of values players have for their bundles. This may seem out of the blue, but it's actually, there are results about this when you have divisible goods instead of indivisible goods. So this is motivated by results in cases where goods are divisible. And what we're able to show and work with Yanis Karagiannis and many others, I'll give you the full reference at the end, is that the MNW solution, the maximum Nash welfare solution, which maximizes this product, satisfies envy freeness up to 1 good and Pareto efficiency. Now, let me pause here for a minute and tell you a bit about why I'm so obsessed with these axiomatic properties. So if you go to Split It and you go to the website, the page for dividing goods, you'll see this thing as part of the page. That's the explanation of the fairness properties. So the illustrations are actually animated on the real page. But the important point is the text. So envy freeness, for example, we explain what envy freeness is, and we explain what envy freeness up to 1 good is. And when a user gets a solution, we give him a personalized explanation for why his solution satisfies the advertised fairness guarantees. Okay, so I believe that this plays a big role in why people are willing to accept these solutions. I mean, the fact that we can give these provable fairness guarantees and explain to people what they're getting and why they're getting it when they actually get the solution. A cool thing about maximum Nash welfare is that it magically achieves these guarantees organically. So before, when we talked about envy freeness, we said maximize the minimum utility subject to envy freeness. Here we just say, just maximize this pretty natural optimization problem without any constraints, and the fairness guarantees somehow magically fall out of that. And that somehow makes the solution really compelling in the sense that when you just look at particular examples, it just does the right thing on every example. And I've looked at many examples, it just always does the right thing. And I'm sort of convinced at this point that this is the ultimate solution for dividing indivisible goods, but I might be proven wrong in a short time. Okay, so going back to the guarantees of the solution, we give these nice axiomatic properties, but in addition, we talked before about the maximum share guarantee, and we sort of forgot about it for 15 minutes. So let's go back and I'll tell you what this solution achieves with respect to that notion. So what it does is it gives each player an alpha n fraction of their maximum share guarantee, where alpha n is order of 1 over square root of n. So it's a non-trivial guarantee. It's maybe not a super exciting guarantee in terms of like, this fraction does go down with the number of players. However, in practice, it actually does really, really well with respect to this measure as well. So if you look at the real instances on Split It, what this is showing is that on almost all instances, everybody is getting their full maximum share guarantee. So on the x-axis, it's like what's the minimum fraction of the maximum share guarantee any player is getting when we apply the MNW solution. The y-axis is the percentage of instances. So you can see that like full maximum share guarantee is like 95.3% of the instances. And then on almost all of the remainder, it's like at least 0.9. And on all of the instances, it's at least 0.7. Right? So even with respect to this notion of fairness, maximum share, the maximum Nash welfare solution does really, really well in practice. Now, another thing you might worry about, and some of you must have noticed this, is that computing the maximum Nash welfare solution is NP hard. It's a very, very easy reduction from partition, for example. And it's one of these problems that is difficult not just in theory, but also in practice. So we actually worked quite a bit on coming up with a scalable implementation to compute this. It did require quite a few engineering tricks. On a high level, it's based on integer programming, but just doing the naive thing works very poorly, and you need to go a few steps beyond. But the good news is I think the algorithm that we ultimately came up with works really well. So this shows the running time in simulations on split-it-like instances. On split-it, we see roughly 3 times as many goods as players. This is what we have here. And you can see that even with 50 players, which is much more than what we see on split-it, the running time is under half a minute. The biggest instance that we've ever seen in practice was 10 siblings who got in touch with us directly by email, because entering this kind of instance on split-it would be very difficult. They had 1,400 items, inheritance, and they sent us an Excel spreadsheet with values for the 1,400 items. And the algorithm took under 10 seconds on this instance. And this is by far the biggest instance that we've seen. So the algorithm definitely does the job in practice for what we need. But definitely, if you needed to do this on a larger scale, with more players especially, the complexity mainly scales badly with the number of players. So things might get bad. Cool. So that's all I wanted to say about fair division. I want to use the last 10 minutes or so to talk about social choice and voting. So the second website is Robo Vote, which is a voting website. It was launched in November 2016, so pretty recently. And its goal is to help people make group decisions, aiming for pretty small groups. Now, there are 2 types of applications on Robo Vote. One is aggregating subjective preferences. So these are cases where people would be happy to a different degree with different outcomes, and the point is to make people as happy as possible overall. So you can think about choosing which movie or which restaurant to go to as a group, choosing a family vacation spot, choosing which paper to give an award to at a conference. That's arguably in the space, but right? So these are all cases of subjective preferences. The other type of application is objective opinions. So these are cases where there's an objective way to compare different alternatives, but that voters don't know what this ground truth is. So they have noisy estimates of the quality of different alternatives. And what the voting process tries to do is to pinpoint the best alternatives, or the actual ground truth, given these noisy estimates. So an example I like to give for this is a group of managers and engineers trying to decide which product prototype to develop, let's say a mobile phone prototype, based on some objective metric like projected market share. So this is not about what you would want to use yourself. It's about what would be the most successful on the market. And of course, there is a ground truth. If you chose prototype A, it would have a 20% market share, whatever, and so on. But you can only choose one prototype, so you can't know what's the truth. And so this is really a perfect example of objective ground truth, noisy estimates, trying to find the best outcome. Another example might be movie executives trying to decide which movie script to produce based on projected box office revenue and so on. So these are all examples where you don't know what the truth is, and you try to estimate it and find one solution based on all of these noisy estimates. So I want to tell you in a few minutes about how we do this. I'd like to illustrate this first with how we don't do this. So this is a story that appeared a few days after RoboVote was launched in this shady British tabloid called the Daily Mail. And what they say is, so for subjective questions, RoboVote gives each rank a happiness value to determine the result. We do not do that. For objective questions, RoboVote tries to estimate the true ranking using statistical approaches. We actually do not use statistical approaches. And finally, the header is RoboVote looks at the pros and cons of arguments to settle debates faster. We definitely do not look at the pros and cons of arguments. The arguments are just the alternatives are given to us as text. We have no idea what that text is, and we just use the rankings in order to determine the truth. So basically, every word of this headline and subhead are completely wrong. So here's, in a few words, how we approach this problem. The starting point is actually in the 18th century and the work of the Marquis de Condorcet. So he had a very naive view of politics and elections. He said, well, voters are think of these enlightened voters that are trying to do the best thing for everybody, and there's like a true quality for different candidates for, let's say, president, and the voters are trying to estimate that quality but make mistakes. So it's a very naive view of politics, but a good fit for the kind of applications we just talked about for objective opinions. And what he said was, the way voters vote would be on a high level. They would give you a ranking, and the probability of giving some ranking would decrease with its distance from the true ranking. So the further away you are, the less likely it's going to be. And from this viewpoint, the goal of a voting rule is to be a maximum likelihood estimator, to choose the ranking that's most likely to coincide with the ground truth. So this is a really cool viewpoint, especially for the 18th century where probability theory was just getting started. But its main flaw is that the optimal voting rule is specific to one noise model. So you have to decide what the noise model is, and then you give the optimal voting rule. But no, and this has been shown in experiments, no one noise model is really consistent with real life. So one step that we took to alleviate this was to say, well, instead of one noise model, we're going to have a wide family of noise models. And we want to do well with respect to all of them. But we're going to relax the kind of guarantee that we want. Instead of this MLE kind of thing, we just want to give statistical consistency. As the number of votes goes to infinity, we want to be able to pinpoint the ground truth with probability that goes to 1. Now, this is cool for crowdsourcing applications where you might expect many votes. But for something like Robo Vote, where we have, like in almost all instances, less than 10 voters, this would be a pretty bad idea. So the direction we actually ended up going in is a worst-case approach, where we said, forget about statistical assumptions in general. We're not going to assume any structure about the noise. We're just going to assume a bound on how much noise you have overall. And then from this viewpoint, what we want to do is choose an outcome that is the closest possible to any feasible ground truth, that will be closest to a ground truth in the worst case. So we can give some nice theoretical results about how close you can get. But the cool thing is that this actually works really well in practice on real data. And for that reason, that's what we ended up implementing on RoboVote. OK, so I want to finish with kind of a motivational slide. So I think there are two ways in which this kind of research can make a societal impact. One is what I call indirect interaction, which is reaching out or interacting with some large organization that works with many people and convincing them to use your state-of-the-art methods. So there are definitely very big success stories in this area. In economics, for example, a great example is the work of Al Roth, who won the Nobel Prize a few years ago, and work in market design and matching. So, matching residents to hospitals, students to schools in many cities in the US, kidney exchange, like all of that came out of this work. And like very significant big organizations are using these state-of-the-art methods. I've also had like quite a bit of experience in this direction, but it's very, very hard and frustrating. So you have all of these politics and very weird obstacles, and things usually go very slowly. So this can be very, very difficult. The other approach is what I call direct interaction. And here the idea is that you just put up a website, and hopefully not for profit, hopefully free, and people just start using it. And the great thing about this is that you can do whatever you want. You can just take the methods that your research tells you has convinced you that are the best and put them out there on the website. And I think this has worked really nicely. So, Splitit, for example, has had 113,000 users as of yesterday. So people are using it quite widely, and I think benefiting from it. But another cool thing about this is it's kind of a cliche, but there is this feedback loop where people use the website, give you feedback, and this has given rise to many interesting problems, both problems with the applications that we talked about and people suggesting completely new applications. So this has actually led to a lot of really interesting research for me. And the whole thing has been super rewarding. So I really want to encourage you, especially the students in the room, to think about how you can put your research out there and get people to actually interact with it. OK, so I just want to finish with the bibliography that I've been promising you throughout the lecture. So the RAND division stuff is based on work with Kobi Gal, Moshik Mash, and Yair Zik, and going to appear in JCM, and it was in EC16. the work on the maximum share guarantee is work with David Kurokawa and Junxing Wang, which will also appear in JCM and was in EC14. The work on the maximum Nash welfare solution is work with Yanis Kargianis, Dave Kurokawa, Helve Moulin, Nisarg Shah, and Junxing Wang in EC16. The work about worst-case approaches to aggregating objective opinions is work with Nisarg Shah and Yair Zik in AIJ. And finally, if you want to find more about computational social choice, we just published a book last year called The Handbook of Computational Social Choice. The book is freely available online, so if you're interested, you can go to my website, find the link easily, and you'll have access to the entire book. Thank you very much.
Thank you, Ariel. I think we have time for a few questions now.
Yeah.
Thank you for the very interesting talk. I suppose I know the answer, but I would like to ask about the first part. Are these mechanisms truthful?
Excellent question. So the question was, are these mechanisms truthful? And it's actually relevant not only to the first part, also the second part. So the answer is no, they're not truthful. However, there are several good reasons why that's okay. So the first reason is theoretical. In many of the applications we talked about, you actually provably can't get immunity to manipulation, strategy proofness, together with the properties we talked about. Like in render vision, you provably can't get envy freeness together with strategy proofness. So if you want these fairness guarantees, you just can't get these game theoretic guarantees. The second part of the answer, which I think is more compelling, is that I don't think it makes a big difference in these applications. And the reason is that what we try to do, what we focus on, is explaining fairness guarantees to people. What we don't try to do is explain the algorithms to people, the allocation methods. And for the main reason is that they're just much more complicated. It's going to be difficult for people to understand these algorithms. So we give a short explanation and refer people to the paper, but I imagine very few people would read the paper. And the thing is that when you don't know what the allocation method is, it's very difficult for you to manipulate because you can't predict how changing your report would affect the outcome. So I think on Split It, I'm actually not worried about manipulation. But definitely, if you apply this kind of methods for high-stakes setting with well-informed players, then you might get in trouble. Yeah.
So you said that maximum shares tend to exist in practice, and all your examples are kind of contrived, right? So do you suspect that given any example where maximum share does not exist, you can do a slight perturbation and then always end up with one that exists?
Yeah, that's a good question. So the question was, if we take an example where a maximum share doesn't exist and perturb it a bit, like perturb the values, will it exist? I suspect that's true in some model. I think it's a hard question because it would imply that there's always a very good approximation of the maximum share guarantee, right? So if you could always perturb the value slightly and get the full maximum share guarantee, for the original values, that same allocation would give you a very close approximation of the maximum share guarantee. So that would be harder than answering that question of like, what's a very good approximation of the maximum share guarantee? The state of the art for that question right now is 3/4. So we prove 2/3. There are several papers that prove 2/3 using different proofs. So for a while, I thought 2/3 was the truth. But now there's a new paper on archive by Muhammad Taghi Khadjagi and his students from Maryland that gives 3/4, using a very, very long and complicated proof. But again, like even to get to 3/4, you need to work extremely hard. Going above that would be very hard, and that would be necessary in order to answer your question.
More questions? I have one, if I may.
Of course.
So I wonder if there's a difference between algorithmic fairness and the human perception of fairness. Mm-hmm. We all think of fairness in different ways situationally, whether it is distributing Picasso paintings or whether it is figuring out which restaurant to go to.
Yeah.
And it seems like the context in which we're playing this game might perhaps affect our perception of fairness. Mm-hmm. Have you experienced that? So, for example, if I raise the stakes from dividing, $10 items to $100 items to $1,000 items, could some of these perceptions change?
Yeah. So the question was, how does the algorithmic results, how do they depend on the context in which people, perform the task, and how How does that, would it change like people's perception of fairness, for example? I think that there's, people, like you said, do things in a certain context, which is different from just getting the result from the algorithm. I would say the context is important. Also, the way, the process by which they do things is important. So, for example, people might negotiate over what the right allocation is, whereas when you just think about what you call algorithmic fairness, which I think you mean, the outcome, just the outcome of the algorithm, that doesn't take into account these human aspects like negotiating over the solution. So the way I think about it is those aspects should be part of the process in the sense that when people use split it, the outcome can be a starting point for some kind of process where people negotiate and take into account some of the aspects that are not captured by the algorithmic fairness only. In fact, there's a paper under submission by a colleague of mine, Min-Kyung Lee, who's an ACI researcher. So it's a study I'm not involved with, but she showed me the paper. So it's a study they did on split it, where but the main thing is they tested the value of adding a negotiation phase after you get the results from split it. So it's exactly what I just mentioned. And they do show a significant benefit in how people perceive the level of fairness when you add this on top. Right, so that's not captured formally in the algorithm, but she has shown like in these human subject experiments that it plays a big role. So I think that's one aspect of it. Like there are aspects that are not captured by the algorithm, but you could still get even if you use the algorithm, because that could be a starting point for a process.
All right, let's thank the speaker.